So to shift the graph of y equals f of x up by a number, what do we do with the function? So the equation of the function.
You have a positive k value.
What does that mean? What is k? What do we do to our formula? So if we start with f of x and we want to shift it up by a number, what do we have to do?
Squared plus
So we add the number, right?
yeah.
So we add the number to the output. So in other words, our new function is y equals, so the output of our old function was f of x. And then we'll call this, I don't know, hk, we'll call k. What about down?
Just do the opposite.
Right, so we subtract it from the output. So subtract the number from the output. So our new function is y equals f of x minus k. And the key here is where we're doing the operation. So here, notice we're doing the operation on the output. So the output of the x squared function is x squared. So if we start with x squared and then we add 3, that's going to be a vertical shift, right? Because we started with the output and then we transformed it. So the difference between that and going left and right is what? So if I want to shift the graph right, what am I going to do?
X minus something, and then it's x parentheses squared.
Right, so we're going to subtract the number from the input. Right? So if the input of x squared is x, before squaring, we're subtracting a number from x, and then we're applying that squaring function. So, and that's true of all transformations. Any operation you do on the input before squaring or square rooting or cubing or whatever our function is going to affect it horizontally. And any operation that you do on the output, so after that operation, is going to affect it vertically. So our new function here would be y equals f of x minus h. So notice that in the parentheses, this is the input of the function f. So I've changed my input from x to x minus h before applying my function. What about if I want to go left?
Add.
2? Yeah, good. So again, my new function is going to be y equals f of my new input that I get after adding. And in general, we won't have this like we're assuming that k and h are positive numbers here. So like when we subtract, we're subtracting like 5. When we add, we're like adding 5. In general, we're just going to have one operation there and then let h and k be either positive or negative depending on the direction that we go. That way we don't have to have like 16 different possibilities as far as like what sign is in there. So if I want to reflect the graph across the x-axis vertically, what did we do?
You multiply by, like, good way to describe subtract, multiply times a negative.
Yeah, it's like multiply by -1, right? So is that do we do that with the input or the output?
Input.
So are we doing this? So it looks like this, right? So when you want to know if it's the input or the output, think of order of operations. So does multiplying by that -1 happen before I square or after I square? If we were to plug a number in for x, the first thing you do is what for this one? And then multiply, right? So we're multiplying -1 by our output. So multiply. So the new function would be y equals the opposite of f of x. And again, I'm kind of leaving out that x squared here and just calling my function f of x because these transformations apply to any of those foundational functions, or really any function at all. If you take any function and you perform or you operate on either the input or the output, you're going to affect the graph in the same way. So what about making it taller, so stretch or compress? What am I operating on? The input or the output? Yeah, the output, right? When you guys looked at these, you had something like 2x squared. And so order of operations would say square the input first and then multiply by 2. And so we are multiplying after squaring, so we're affecting the output. So multiply a constant. A constant's just like a number. So by the output. So our new function is, y equals a times f of x. And we can combine these operations. Again, you just want to think of order of operations as far as like when you do each of these. So the shifts affect where that vertex is, but the flips and compressions and stretches, they just affect like what your y values are essentially. So I always look at the shifts first because your vertex is normally 0, 0, right? So it's not affected by multiplying by anything. It's only affected by adding and subtracting. So I always look at shifts first, and then I do my stretches and compressions and any flipping I have to do. Notice that we did not do horizontal stretches and compressions, and that's because any horizontal stretch or compression can be achieved by a vertical stretch or compression, right? Like we can make it wider by stretching it vertically. And as far as in practice actually working with the function itself, it's a lot easier to simply like throw a ×5 on at the end, like multiplying by the output, than to try to figure out how to coordinate the stretch and shift horizontally. It gets a little funky as far as having to multiply by like weird numbers and a lot of parentheses. So we achieve all of our stretches and compressions vertically to avoid the messiness of having to do it horizontally. So if I want to make a graph 4 times as tall, and I want to shift it up 1, both of these are acting on the output. So I'm going to start with the output of the general function, which is x squared. Order of operations says multiply and then add or subtract, right? So I am making it 4 times as tall, and then I'm shifting it up 1. That make sense? Yes.
So I thought it would be like moving it up 4 on them, but then
So you're absolutely right. Like they go on forever, so you can't actually make them taller or shorter. So what we mean when we say 4 times as tall is we mean that like the one I always look at is like normally we have a point at 0, 0, that's our vertex, and then this next point is 1, 1. And so this distance is 1 unit. So when we say 4 times as tall, we mean take that distance and stretch it to 4 units. And so we achieve that by multiplying that y value of 1 by 4. So think of stretching like just like a small portion of the graph, because you're absolutely right. Like the whole thing always goes on forever, so you can't actually make it taller. But it's kind of like a rubber band. Like if you nail it at the vertex and then like pull the whole thing, it just stretches it. And so that's all they mean by that.
thank you.
Uh-huh. So if I want to shift it 3 units right and then reflect it across the x-axis. So this is horizontal and this is vertical. So I'm going to start with my input, which is x, act on that to get my horizontal transformation, then square it and work on my vertical transformation. So any operations you do before squaring are going to be horizontal transformations, and any operations you do after squaring are going to be vertical. So I'm going to start with my input. What should I do to my input to shift it 3 units, right? Subtract 3. And then I'm going to square that whole thing and then flip it. And if you wrote -1 there, that's totally fine. If you have a flip and a stretch, so like if I was going to stretch it by 4, by a factor of 4 and flip it, I would just have a factor of -4 out front. So I would just make that stretch factor negative to flip it as well. Okay, you guys try the next one. Or rather, go ahead and do the next 2. Okay, what'd you get for C?
I said -2/3 x squared.
Perfect. Right, so both the reflection and the, in this case, compression are vertical. So we're going to multiply by 2/3 and then take the opposite of it to do that flip. And then what about that last one?
I did x plus 5 squared minus 2.
Good. So inside those parentheses, acting on our input, that's going to shift it to the left 5. And outside the parentheses, that's going to make it go down 2. Notice that the operation that we use for horizontal transformations is the opposite of the direction it's going, as opposed to vertical, it's the direction we think it should go. And the way I remember that is like if you're trying to find y, you like plug a number in for x and you do the operations that are given, right? But if you're trying to solve for x, you have to undo all the operations to get x by itself, right? So we always do the opposite on x and the non-opposite on y. I don't know how to say that. But we do what we're told to do with y, and then we do the opposite of what we're told to do with x. Any questions before we move on to quadratics? Yes.
So I'm just writing little notes on each of these.
Mm-hmm.
When you square it, does
Yes.
that have, when you're saying like the negative is to flip it on the outside of
Yep.
the parentheses, when you square it, what does that stand for?
So the original function is x squared. So like squaring it is just making it into a transformation of the x squared function. So like everything that we do other than squaring it is what's going to stretch it and move it and flip it. But the x squared itself is like what we started with.
Okay, I just want to make sure.
So that's like our base operation.
Okay.
So like if instead of x squared, I put x to the third right here, that would be the graph of x to the third shifted up 1 and stretched by a factor of 4.
Different. Okay.
Right, it's so like we can start with any of our base functions and use these transformations to transform that graph.
Okay. Thank you.
Okay. So this was in your video notes, but I just want to make sure that we're all super clear on all the different forms and how we use them, because as we start writing quadratic functions, we have to choose which form it's going to be convenient to write it in based on the information that we're given. So when we have general form of a quadratic function, the interesting thing that tells us, just without doing any calculations whatsoever, is the y-intercept. As far as when you write quadratic functions from information that's given, you will like never ever use the general form because, because it's a pain in the booty. It's like you can't just start with the y-intercept and know everything about the graph, right, or about the equation. And so you have to do quite a bit more work if you're going to use the general form. So we don't typically write equations in that form from the get-go. Factored form of a quadratic function, the interesting thing that this gives us is the x-intercepts. So our x-intercepts are m0 and n0, which means when it comes to writing a quadratic function, if you're given the x-intercepts, you immediately want to think factored form, because then it's just a matter of figuring out what a is, because they gave you that m and n. And then standard form gives us our vertex. So same deal, if you're given your vertex and you want to write a quadratic function, the first thing you should think is, oh, I need standard form, because then you know your h and you know your k already, and you just have to find your a. So my vertex is h, k. Another thing to notice about these forms is that a is always the same. So if you know what that leading coefficient is in one form, it's going to be the same in any other form. So a never changes, regardless of what form it's in.
A factored form?
Yes.
Would the m and n be negative if it was x plus m?
Yeah, so if it was like x plus 3, that's the same as x minus negative 3. Mm-hmm. So your m would be negative 3. The same is true with like the h down here. If I had a negative x coordinate for my vertex, it would look like this, right? Because it's just like subtracting a negative. Great question. Thank you.
Thank you.
Any other questions just on the forms of the equations? Yes?
Is m still the slope in that one?
No, great question. So remember that only linear equations have slopes.
Oh.
So these are quadratic, which means that they don't have a constant rate of change. And so, yeah, the m just means something different here. It's kind of silly that they do it this way, but it's also true that this is not the y-intercept. Now c is the y-intercept. Mm-hmm. So the way I think of it with any polynomial equation, which includes quadratics and linears, is that the constant term is, if it's fully simplified, the constant term, so the term that doesn't have a variable in it, that's your y-intercept. And that way we don't have to connect it to like specific letters. Of course. Other questions? Okay, let's talk a little bit more about general and standard form. So we've got an equation here or a function. What form is it in? Yes, this is standard form. When I was a wee one, way back when, general form was called standard form, and standard form was called vertex form.
Oh.
Yeah, so that's not confusing.
I think that's why I have problems.
What's the vertex?
2 negative 9.
Very close. Remember that with x's, we always do the opposite, right? So that's going left, negative 9. Notice that standard form of a quadratic correlates to what we just did with 5.1, so with all those transformations, right? So if you look at standard form of a quadratic, this guy is just the x squared function shifted right h units, up k units, and then stretched by a factor of a. And so that's why our vertex is hk, because the vertex of the x squared function is 0, 0. And if you move to the right h units, then your x coordinate becomes h. And if you move up k units, then your y coordinate becomes k. So that's really all standard form is just that transformation of the x squared function.
So if it was x minus 2,
It would be
it'd 2
positive.
negative 9?
Yes. Yep. So we always go the opposite direction in the horizontal direction. So does the parabola open up or down? It opens up. Good. And that's because A is positive. Remember from what we just did with transformations, if there's a negative, that means we had a reflection. And so it flipped downward, so then it opens down. You ready for my cheesy mnemonic device? When you are feeling positive, you smile. And when you are feeling negative, you frown. Like so, and like so. Okay, that we'll never forget. That works for second derivatives too when you get there, for concavity. So how would I find my y-intercept?
Set x to 0.
Yes, very good. And this is something, if you take nothing else away from this class, take this. For every single function, no matter what kind of function it is, and every single equation, no matter what form it is in, to find the y-intercept, you make the input 0, and to find the x-intercept, you make the output 0. No matter what. Like that's just because every point on the y-axis has an x-coordinate of 0, and every point on the x-axis has a y-coordinate of 0. So that is always true. It has nothing to do with what type of function you're working with. Often people try to remember different things about different functions. You don't want to remember the same thing in different ways for every single function. So that's something that's true of every single function. So we are going to evaluate f of 0. So we're making our x value, our input, 0. So we've got f of 0 equals 4 times 0 plus 2 squared minus 9. What is that, 7? So f of 0 is 7, which means that my y-intercept is 0, 7. Remember that intercepts are points on a graph, and so they have an x-coordinate and a y-coordinate. So you don't want to just give the y-intercept as 7. You want to give it as the actual point. You'd be surprised how many people on tests are like, oh, the y-intercept is 3. Where's that? Because it's not an ordered pair, right? It's like the 911 thing. I've told your class about the 911 thing, right?
Yeah.
So when they first came out with 911, it was the big ad campaign was call 911, right? And I mean, there's a huge campaign. And then people would get in like an emergency situation and be like, I can't find the 11. I mean, because you panic, right? And people are like that on tests too. So you want to just be as specific as you
And then
can.
You get stuck.
So, right? And then you get stuck. So if you're super specific, then you can always, even if you're panicking, you can always figure out what exactly you're supposed to do. Okay, we're going to express this in general form. How will I do that?
Just expand it.
Yeah, we're just going to expand it. So general form is like the fully simplified form. It just means do all of the operations that are in that expression. So we're going to multiply this out. So f of x equals 4 times x plus 2 squared minus 9. Can I distribute that 4 first?
Nope.
No, because I have to do exponents before multiplication. And so we're going to write this out as x plus 2 times x plus 2. Note that x plus 2 squared is not x squared plus 4. We call that the freshman's dream. Everybody really wants it to be true, but no matter how hard we try, it's just not. So we have to distribute like x times x times 2, 2 times x, and 2 times 2. We can't just square the x and square the 2. So when you have 3 factors like this, I'm going to multiply x plus 2 times x plus 2, and then I'll distribute the 4. So I need the result of x plus 2 times x plus 2 in parentheses. So this is x squared plus 4x plus 4. And then we'll distribute that 4. So f of x equals 4x squared plus 16x plus 7. And notice our y-intercept is represented there as the constant term in general form, right? Just like the one we found. What's next? Ooh, we get to graph it, which we know how to do now because we just did all those transformations, right? So what is this? F of x equals 4 times x plus 2 squared minus 9.
You skipped finding the x-intercept. E.
That's funny that. Okay, let me just make a new page. Sorry. There we go. Okay, let's find the x-intercept. I wondered why they weren't asking us that.
It's right above the graph.
Thank you.
Yeah.
X-intercepts. So again, we are plugging 0 in for our output. So we are essentially solving f of 0, f of x equals 0. So that just means replace that f of x, the entire left side of the function, with 0. So we have 0 equals 4 times x plus 2 squared minus 9. So when you've got this in standard form, please save yourself some time and do not multiply it out just so you can use the quadratic formula. Everybody's so addicted to the quadratic formula. But this one we can do just like we did, we solved like way back when, right? Like the first week, like it was so long ago. Like the first couple days, right? Remember where we can undo that exponent of 2 by taking the square root? So we just want to get the exponential portion of this, so this guy, all by itself first, and then we can take the square root of both sides, and it's a whole lot quicker than multiplying it all out and then using the quadratic formula. So we're going to add 9 to both sides. And then divide both sides by 4. And then we can take the square root of both sides. Remember, because we have an even exponent, that we get both a positive and negative square root. So x plus 2. So we get plus or minus 3/2 equals x plus 2. And so that means -2 plus or minus 3/2 is equal to x.
Would it be square root of 3/2?
Well, so when we take the square root of 9, we get the number 3. So we like use up that operation.
Gotcha.
And then you can throw those in your calculator. Let's see. -2 plus 3/2 is going to be -1/2. And -2 minus 3/2 is going to be -7/2. Right, because 2 is 4/2. And so my x-intercepts are -1/2, 0, and -7/2, 0. Good stuff? Okay, now let's graph. So what do I have to do with the x squared graph to get this one?
Move it to the left by 2 units.
Mm-hmm.
Switch it by 4 and down 9 units.
Mm-hmm. I don't really like using L and D. That's weird. I'll do an arrow. Left 2, down 9, and then we're going to stretch it by 4. So we'll just start with the vertex. So the vertex is going to be at -2, 9, right? So, I'm sorry. -2, -9, right here. And then remember when we said that that stretch by 4 takes that point that was 1 unit to the right and 1 unit up from the vertex and just makes it 4 units up instead? So instead of having a point here, like I would if it was just a transformation of x squared, I'm going to have a point 1, 2, 3, 4 units up. And because parabolas are symmetric, I'm also going to have one over here. So that's that stretch of 4. And then since we found the x-intercepts, we might as well use those to our advantage. They're right there and right there. Our y-intercept is not on here, so we don't have to worry about it. It doesn't go up to 7. So now we just have to attempt to make this sort of pretty. The only thing I really look for as far as like how nice your graph is that you gave me a U and not a V. Like there shouldn't be anything pointy on these graphs. So you don't want to be like this and then like extend it. Just make sure that's a nice curve down at the bottom and that it doesn't come like back in at the top, right? That you're ever so slightly moving in the outward direction. Okay, quadratic formula. You must memorize the quadratic formula if you haven't already. My trick for memorizing things is to put it on a Post-it note on your dashboard and you read it out loud to yourself every time you stop at a stoplight. It works. Some people like to put it in their shower and read it to themselves. The other thing you can do is just every time you use it, write it down. Like before you actually plug numbers in, just write that statement down like as your first step before you actually use it. If you do that like 10 times, you will probably never forget the quadratic formula. And there's a super interesting video on WebAssign of where the quadratic formula came from. I usually do it in class, but we're pressed for time, so we're not going to do it in class. But I think it's super interesting where it came from, because it's like the whole upshot of it is it's not that exciting. Like, it's not some big feat that some guy discovered and like everybody was like, wow, you're amazing. That's why it's not named after anybody. It really is just taking a general equation and solving it, and then saying like, hey, if you put this number here and this number here and this number here, you get your solutions. So you should watch the video. It's sort of interesting. Did I say we were going to do 5-2 before or after? Okay. Part 3. And then we'll take a break, I promise. So we're just going to briefly look at the relationship between average rate of change and quadratics. So we know that with linear functions, we have a constant average rate of change. And this thing we call the first difference is basically just the slope when it's a linear function. So it's the difference in the y values between two consecutive points. So when my x value goes from 0 to 1, my first difference is whatever the difference in the y values is. When I go from 1 to 2, same deal. So if we look at these two functions, I want you guys to go ahead and fill out this column, this column, this column, and this column. So to get that first column, you're just plugging the x values into your function. And to get the second column, you are finding the difference between those two y values and those two y values. Make sense? And then we'll do that last column together.
Sweet, thank you.
Where's the back side?
No.
Oh, so for this, sorry I made a mess, but that, I just had 2 out of the 3
Yep.
things.
Perfect.
Is that good?
Yep, that's awesome. Thank you.
Mm-hmm.
Okay, do we all have something that looks kind of like this? If you didn't get that far, you can just copy mine. So we know that linear functions have a constant average rate of change, right? And so that means that the difference in the y values between any 2 points where the x value goes up by 1 should all be the same, right? So this constant first difference is just another way of saying that linear functions have a constant average rate of change. Now, over here with a quadratic, as we would imagine, like the first difference isn't the same, right? Because we don't have a constant rate of change with a quadratic. But one of the interesting things about quadratics is that even though the rate of change is not constant, the rate of change of the rate of change is constant, which means that if we calculate the second difference of a quadratic, which means the difference of the first differences, we find that that is constant. So notice that the difference between 3 and 5 is 2, and the difference between 5 and 7 is 2, 2, 2, 2. And that's true of all quadratic functions. So the rate of change isn't constant, but the rate at which the rate of change is changing is constant. And so we have this constant second difference. And that's a unique property of quadratic functions. So just like yesterday we had a couple tables and we had to tell if they represented linear functions or not. You guys remember those? By finding the rate of change between several points. So we can, if we find that one of those tables does not represent a linear function, we can then calculate the second differences to determine if it represents a quadratic function. So with these tables, there's several different ways we can look at them to narrow down what type of function they represent. And sometimes it's none of the above, right? Sometimes it's just a bunch of random points. But this is a way to identify a quadratic function. So I think we covered all of this already. No quadratic functions do not have a constant average rate of change. The first differences for G, they all differ by 2. And these are all the same. Oh. Questions? Be careful when you're given a table that before you start calculating these differences, that your y values all differ by 1. If it skips around, then when you subtract your y values, did I just say y values twice?
Yes.
Make sure your x values all differ by 1, because if your x values skip around, then the change in your y values isn't going to tell you anything interesting, right? Like the change in the x value has to be constant to compare the changes in the y value. So just make sure that it's actually going up by 1s when you do this process. Okay, so we're going to graph these guys. It says use technology, but we don't really need technology, right? Because we have all our transformations. Let's see, this looks something like, if I plug 6 into that, I get, what, 19? So, start at 1 way down here. So there's our linear function, roughly. And then this is going to be kind of ugly, I bet. So 0, 1, 2, 1, 4, 2, 9. 4, 2, 9 is like right here. 3, 16 is like right here. 4, 25 is here. 36, 49. Let's pretend it goes through all the perfect points. So if we look at the rates at which F and G increase, right, we notice that this is increasing at a constant rate. And then this one is increasing at an increasing rate. So it's increasing because it's going up, and it's increasing at an increasing rate because it's getting steeper. So the rate of increase is itself getting bigger. So it's getting steeper as we move to the right. So it is increasing at an increasing rate. So it's kind of like acceleration. So when you're driving forward, that's like your distance is increasing, right? But if you drive forward at a constant speed, then the distance that you're going is increasing, but it's always increasing at the same rate. Whereas if you're hitting the gas, the distance that you're moving is increasing at an increasing rate, because not only is your distance increasing, but your speed is increasing as you move. So that's going to be like our parabola, where it gets steeper and steeper and steeper, as opposed to just going at the same rate all the time. Okay, we're going to stop there and take a break. So we'll come back to it and look at it if we have time, but I think that talking about maximizing and minimizing is more important at this point. So when we talk about optimizing quadratic functions, like all we're talking about is finding that local maximum or local minimum. So remember that every quadratic looks like either this or this. And so the vertex of the quadratic, of any quadratic or any parabola, is either a maximum or a minimum. So minimum or maximum. And notice that each quadratic only has one of the two, right? Like, so either it has a maximum value or it has a minimum value. It doesn't have both, although sometimes the constraints of the problem will cause our domain to end at a certain spot. But for our purposes, we're focusing on finding either the maximum or the minimum based on the vertex. And the process is going to be the same regardless of if we're finding the maximum or the minimum, because we're really just finding the vertex of the parabola. What's going to determine if that vertex is a maximum or a minimum is A, right? Remember, if A is positive, it opens up, and if A is negative, it opens down. So if it opens up, the vertex is going to be a minimum. It's going to be the lowest point. And if it opens down, then it's going to be the highest point. So let's start just with finding the max and min of these functions just before we start talking about applications. So this statement right here looks a little bit complex, but all they're saying here is that you can find the x value of your vertex by plugging a and b into that formula, and that you can find the y value by plugging that back into the function. So we want to know if it has a max or a min. Will this one have a maximum or a minimum?
Maximum.
It'll have a maximum because it opens down, right? So A is negative. So that means we're going to have a maximum. And so now let's find the maximum or minimum value of the function and the x value at which it occurs. Notice that in this statement, they say it in the opposite order that you will find it. You always find the x value first because that's what the vertex formula gives us, and then we'll plug it back in to actually find the maximum value. So to find the x value of our vertex, we have x equals the opposite of b, so negative 2 over 2 times, in this case, that x squared over 3 is the same as multiplying x squared by 1/3. So our a is really negative 1/3. And this is one of those places where I really don't want you to spend a whole bunch of time or effort like calculating this. So let's learn how to use our... So x equals 3. So now to find our y value, we're going to evaluate the function for an input of 3. So we've got f of 3 equals negative 3 squared over 3 plus 2 times 3 plus 7. I think that's 10.
Me too.
But plug it in your calculator and make sure I'm not losing my mind. And so the vertex is the point 310. Which means that the maximum value of f is 10. And it occurs at, I prefer to say x equals 3. You could say it occurs at 3, but I like to include that x equals in there, just to be sure we know we're talking about our x coordinate. So you guys try the next one. Notice that in order to use the vertex formula, you guys are going to have to put this in general form. So you'll have to distribute that 2x first, and then use that same process. So make sure you ask yourself first if it's a max or a min, and then go ahead and find that vertex. Okay, go ahead and check your solution and ask me questions if you have them. Couple notation things. Make sure you're including this x equals. I promise when we start doing the application problems, you're going to be really happy that you can connect that number to whatever you said x was in the beginning. Because when you start just having numbers float around, it's pretty hard to figure out what represents what. That's why we assign things variables and things like that. Any questions on this before we start applications? You guys ready? Okay. So here's a bunch of words. So these are just recommendations. We already know a lot of this, so we want to, if possible, draw and label a picture. Just different things to help you wrap your mind around what exactly is going on. Again, I've told you this before, but always write what your input and your outputs are, what they represent, and like what variables you're using to represent them. Because as we get more and more functions going on and more unknowns floating around, you're really going to want to be able to have sort of a key to reference back to and be like, oh yeah, I just found X. That means I found the price or whatever it happens to be. So we are going to do, oh, this one's my favorite. So this is a really good example of all the different things that can be going on in a problem. So in this problem, they give us an equation for the price, and they give us an equation for the cost. Remember, cost is the cost to the producer, so the person producing the items. And then we have questions about profits. So the first thing you always want to do when you do these problems is ask yourself what it is you're trying to maximize or minimize, because that's going to tell you what you actually have to write a function for, right? If you maximize the price function, you are finding where the price is at a maximum, not where the profit's at a maximum, right? So if you want to maximize the profit, you have to write yourself a profit function first so that the outputs of the function are actually the things that you're trying to maximize. So in this case, we'll start with input. What does x represent in this case?
Number of discs.
Yeah, so quantity. And then I want my output to be profit. So P of X, be very careful with the P's here because we have lowercase p represents price, uppercase P represents profit. So just be really careful that you know which is which. If I want to write a profit function, how do I do that? So what's the formula for profit? How do we calculate profit?
Revenue minus the cost.
Yep. So revenue minus cost. So I often, with these guys, I kind of work backwards. I'm like, okay, I want a profit function, which means I'm going to do revenue minus cost. And then I ask myself, like, do I have a formula for revenue? Do I have a formula for cost? Cost we have taken care of because we have a cost function right here, but we don't have a revenue function. How do I get a revenue function?
Isn't it like operating costs? I don't know, it's just what you sell, isn't it? Times the quantity.
Right.
Price times quantity.
Yep, price times quantity, good. Sorry, I went off the board there a little. So we know our quantity is what?
The number of discs, which is X.
X, good. And then our price is given by our price equation up here, which is usually, the price equation is usually called the demand equation. So it's the price a consumer is willing to pay based on the quantity, right? We know that demand or price and quantity demanded go up and down with each other. If you charge more, they buy less. If you charge less, they buy more. So we're just going to plug that guy in for price. So negative 0.00041x plus 10. So I've got negative 0.00041x squared plus 10x. So now I'm ready to write my profit function because I've written an expression for revenue and I've written an expression for cost. Well, they gave me an expression for cost. So far, so good? So we've got P of X equals revenue, which is negative 0.00041 x squared plus 10x minus cost. Do you guys have all that revenue stuff written down? I'm going to erase it because I'm going to run out of room to write this whole thing. Yeah? Sorry. Should have managed my space better here. So 600 plus 2x minus 0.00001x squared. All those zeros can get you. So notice that I put both of those in parentheses. The first one, so my revenue, if I hadn't put that in parentheses, it wouldn't have hurt anybody. Because to get rid of those parentheses, notice there's not anything to distribute, right? So like those parentheses we could just drop. I like to put parentheses even sometimes when I don't need them because then I force myself to think about if I actually needed them or not, right? So it's better to have them and then realize that you didn't need them than to not have them and realize that you did. So that second set of parentheses we definitely needed, right? Because to get rid of those, we have to distribute the negative. So you want to be subtracting the entire cost. If you don't have parentheses, you're only subtracting the first term in your cost function. So here we have negative 600 minus 2x plus 0.00001x squared. And now we'll just combine like terms. So p of x equals, somebody want to throw that negative 0.00041 and plus 0.00, what is that? Is that just going to be negative 0.0004? Yeah. And then 10 minus 2 is 8. And minus 600.
So the only thing that changed between your first p of x and your second p of x is the distribution of the negative?
Yep.
Okay.
I just distribute that negative to get rid of the parentheses so I can combine like terms.
Okay.
And now we are ready to actually answer the question, right? So a big bulk of these problems is just getting the function that's going to help you answer the question. And you want to make sure you get your function and simplify it as much as you can. And then at that point, you can be like, okay, I'm trying to maximize the profits. And I want to know how many copies we're going to produce each month. So I'm looking for the quantity that's going to maximize the profit. So anytime you see this maximize or minimize with a quadratic function, you want to think find the vertex. And so that's that vertex formula. So x equals the opposite of b over 2 times a. I'll let you guys plug that in for me. What do we get?
Got 10,000.
Everybody agree? Sounds about right. What are we making? Copies of discs. So, copies. So 10,000 copies is going to maximize our profit. And then it says, what is the maximum profit? So if we want to find the profit, we are going to plug our 10,000 copies back into our profit function. So P of 10,000 equals I'm so running out of room. 8 times 10,000 minus 600. I'll let you guys calculate that too.
So your x equals a negative 8 divided by 2. That's just looking for your x value. So that's your,
That is
what equation did you call it? That's your,
the vertex formula.
okay, let's do that.
So that's just finding the x coordinate of our vertex, which is going to tell us how many copies we should produce to maximize profit.
I got 39,400.
Maximum profit is 39,400. Good. So I've got a question for you. What price should they charge if they want to make this much profit? They want to maximize profit.
Plug it into the price formula.
Plug what?
10,000.
Yeah. Cody, is that what?
I was just gonna say, can you divide the 39,000 by 10,000?
So if the profit was the if that 39,400 was the revenue, then we could divide it by the quantity and that would give us a price to charge. But because that takes into account their costs as well, that's their profit after they've made the revenue, subtracted off all the costs. So it won't give us the price to just divide. But what's cool about these situations is that the input of all these functions, the cost function, the revenue function, the price function, all of them have the same input, which is quantity. So once you've determined the quantity that's going to maximize your profit, you can figure out what the price is to maximize profit, what the revenue is that you'll earn that would maximize profit, right? Just by using that same X value. So we know that 10,000 copies is going to maximize profit. If I want to know what price I should charge to make that happen, I'm just plugging 10,000 in here. And not being able to fit it. My existence. So P equals negative 0.00041 times 10,000 plus 10 gives you what?
4,010 or
Is it $14.10? I do not trust myself with the decimals.
yeah, $14.10.
Oh, I'm sorry. Wait, no, this is negative.
Oh.
So it's $6.90. Nope. $5.90.
This lady.
It's $5.90. So if they set the price at $5.90, they would be able to sell 10,000 units, and that would maximize their profit. So you can find out, once you find that X value that maximizes your profit, you can use it to find all sorts of other things. So then what about this? How many disk copies should I make if I want to break even? What does break even mean?
That cost is equal to revenue.
Yes. It also means that profit is zero, right? So we could do it by setting the revenue and cost functions equal to each other, or we could do it just by setting the profit function equal to zero.
That sounds easier.
So this means that our profit is exactly zero, which means we're at a completely different point than we were before, right? So if this is our profit function, we found where our profit was going to be at a maximum. Now we are finding where our profit is equal to zero. So the numbers that we got, like the X value and all that stuff that we got in the last problem, they're gone now. So we're finding completely different points on the function. So you don't want to bring that 10,000 into play. So I have to remember my profit function. 0 equals negative 0.0004 x plus 8x. Did I get that right?
Yep.
Okay. And when there's decimals involved especially, I strongly recommend that you just use the quadratic form. What's up?
What did the first x be x squared?
Oh, yes, thank you. Good catch. So I recommend, especially when there's decimals involved, that you just use the quadratic formula to solve this. So x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative 8 plus or minus the square root of 8 squared minus 4 times negative 0.0004 times negative 600 all over 2 times negative 0.0004. Don't be a hero. Just plug it all into your calculator all at once. So all you need to plug this entire thing into your calculator, and so you're going to have to do it twice, right? You're going to have to do it once with a plus sign here and once with a minus sign there, although I can show you a nifty way to get one from the other. But you can't do them both at the same time is my point. All you need to put this all in your calculator at once is a set of parentheses around the entire numerator and then a set of parentheses around the entire denominator. Otherwise, you type it exactly as it's written here. Your calculator, depending on what type of calculator you have and how old it is, it might, when you put the square root, it'll like go like this and then give you like a parenthesis. So that means you have to close that parenthesis as well. So like you really have this going on.
So just put the parentheses around both the denominator and
And if you find yourself getting mixed up with all of those parentheses, you don't need these parentheses here. Like, you can just use a times sign. Like, when we actually write these, it's easier to write it with parentheses, but you can use, like, the multiplication symbol between those numbers instead of putting each of them in their own set of parentheses if you find yourself getting mixed up with so many sets of parentheses. We got, and we can round because we're not going to be making partial copies, right? 9,925. So there's two answers here. Copies. 75 copies.
Isn't it 19,000?
Yeah.
Oh, I'm sorry. I was thinking, yes. I was thinking how far it was away from 10,000. Thank you. And 19,925 copies. Realistically, how many copies do you think they would make? So the way we could figure it out is
10,000 copies.
10. Well, they would. You're right. Realistically, they would make 10,000 copies. But if we were thinking about this whole 75 and 19,925 copies, so we know that we break even either way. But in the real world, like, we might have a factory that has a certain capacity, and it might not make sense for it. Like, once we get a whole new factory, if we have a factory with a capacity of like 14,000, it's going to take a whole new factory to get that 19,000, which is going to change that equation, right? Because all of a sudden our costs are different. And so, like, it always seems silly when we do these problems and we end up with like two answers. We're like, but which one's right? Right? And we would need a little bit more information about the particular situation to know like which one they'd actually decide on. But the mathematical model gives us certain things, and then the situation has to provide the information to actually make decisions. So we would, in this case, we would just give both answers because we don't know which one's the right one. Okay, here we go. Vineyard. So this problem, I want to relate back a little bit to one of the problems that we were doing last week because we're going to be doing similar ones, and this is another way to do them that might be a little bit simpler. So like we were talking last week about that whole like you can sell like 50 something or other at like $10 each, right? And we were coming up with these revenue functions. If we, instead of considering our quantity or price to be X, if we think about it in terms of the change in price or quantity, it's sometimes a little bit easier to come up with that function. You just have to remember that your input is the change rather than your price or your quantity, etc. So in this case, I'm going to make X. And I know there's no price or quantity here, but the formulas end up being like exactly the same. It's just a different situation. So I'm going to make X where is it? The number of additional vines. So I'm going to make X the increase in vines planted. So what I mean by that is like beyond the initial 700 that we're talking about here. So if I planted 705 vines, then X would be 5. Does that make sense? So we are talking about maximizing grape production, which means we need a function for grape production. So how many individual grapes are being produced? So let's call that, I don't know, how about g of x?
Isn't it pounds per grape, not individual, or pounds of grapes?
Oh, thank you, not individual grapes, pounds of grapes. Individual pounds of
Like that'd be
grapes
so expensive.
equals pounds of grapes produced. And based on the type of information they're giving us, well, they tell us that each vine produces a certain amount of grapes, like a certain weight of grapes. And then we talk about how many vines there are. So the pounds of grapes produced is going to be the number of vines times the production, well, I won't even use that big word. Let's just say pounds per vine. We good so far? So just in general, we know we can find the how many pounds of grapes were produced by taking each of our vines and multiplying by how many pounds each of them produces. So in order to write this function, I need an expression for the number of vines, and I need an expression for the pounds per vine. Keep in mind that we can't just use 710 because we're theoretically changing how many vines we plant, right? So, number of vines and pounds per vine. So when I write these expressions, I usually do them kind of together. So I say, okay, I've got a starting point, right? So I know that each vine will produce 10 pounds of grapes if I plant 700, right? So my starting point for number of vines is that 700, and pounds per vine is the 10 that corresponds to it. So those two numbers have to correspond to one another as far as the information given. And then it says that for each additional vine, the production of each vine decreases, which means that the number of vines is going up and the pounds per vine is going down. How much is the number of vines going up by? How do I represent that? X, right? Because we said it from the very beginning that the increase in the number of vines I plant is going to be X. So my new number of vines is 700 plus X. And we know that every time we do that, we lose 0.01 pounds per vine. So 0.01 times the number of times, or the number of vines we've increased by. And so now we have an expression for both of those. We can multiply them, and that's going to give us our function. So g of x equals 700 plus x times 10 minus 0.01x. And I usually tell you guys not to bother distributing unless you have a reason to. In this case, we do have a reason to because we're trying to maximize this function. And so we want it to be in general form so we can use our vertex formula. So we're going to go ahead and distribute this all out.
What was the reason for distributing that again?
So in order to maximize, I want to find my vertex. And my vertex formula, that x equals negative b over 2a, is based on the general form of a quadratic. And so in order to use that formula, I have to put it in general form. So I'm going to distribute everything. So minus 7x plus 10x. Definitely correct me if I mess something up. You guys know how I feel about fractions. Or not fractions, decimals. X squared. Right?
Yeah.
So I'm going to put that in descending order because, again, that vertex formula is based on the A and the B and the C. And so I want my A, B, and C to be in order so I don't mix them up. So we're going to put our x squared term first. And then we're going to put our x term and then our 7,000. So now we've got our production function in standard general form. And I can then use my x equals negative b over 2a to find the x coordinate of my vertex. So x equals negative 3 over 2 times negative 0.01. What do we get?
150.
Okay, so what did I just find? Yes. So before we do that, let's think about what x is in terms of the grapes.
Maximum yield.
Is x the maximum yield?
Isn't it the maximum number of vines?
Yes.
Closer. What is x? It's the increase in vines, right?
You're on 700.
Yes.
So how many more vines we can have after?
So 850 vines is going to maximize my yield, right? So that's one thing we have to be careful of. So using the increase as our input can make finding the formula for it a little bit simpler, but we have to always be like referring back to what we said x represented so that we're careful not to say that we're planting 150 vines, right? So we can say that 850 vines will maximize yield, will maximize yield. And then if I want to find my maximum yield, what will I do? Careful. Just the 150. So we have to be so careful because the input of the function is still just x, right? So that g of x tells us how many pounds of grapes are produced for that increase, right? Not for, so if we put 850 in there, we would be saying we were planting 1,550 vines. So you kind of have to go back and forth between this, like how many vines and how many vines, like what was the increase in vines. And so that's why I harp on you guys so much to like write this stuff down so that every time you have an x value or every time you find an x value and every time you're ready to plug an x value in, go back and be like, what am I actually using here? What did I actually find here? Because it's really easy to get it all mixed up. So g of 150. In the interest of space, I'm not going to write that whole thing out. I'm just going to let you guys calculate it and tell me what it is.
I got 7,675.
7,675. 7,675. Does that sound good to everybody else?
Don't take my word.
So maximum yield is 7,675 pounds.
So we don't want to say x equals 150.
Well, x does equal 150,
Okay. But yeah.
which
But
means
we only
that
care about the 150 in terms of it being related to the 700, which is our starting value.
right. So like the x, so the input of our function is the increase. When we actually talk about how many vines we're going to plant, we have to include that original 700.
Okay.
But whenever we use it as an X value, we have to use the 150 because
Yeah.
our function is all based on how much we're increasing it by. And then, so to relate it back to what we did last week, if, remember we had those ones where you know, like 30 rentals at $10 a rental, this would be exactly the same problem, except that like this would be a revenue function, and one of these would be price, and one would be quantity, and this would be like increase in price. So you can do exactly the same process we did here for problems like that to avoid like having to do the table and the whole like X minus 20, and like that was a little bit challenging, I think, doing it where X was the price. So this is just another way that you can approach those problems, is instead of making your input the actual price or the actual quantity, making your input the change, because that's kind of what we're talking about as far as like increasing and decreasing. Any other questions about this one? Okay, let's make a fence.
Whoever makes these problems must really like fencing.
Yeah, I mean, it's just a good example of this type of problem. There was the guy that used to be the student success coordinator for 121, like, I don't know why, got like really into like enclosing slugs. Like he'd like make slug fences because like there'd be like a salt mine on one side, and so you don't need a fence there because like slugs don't like have an aversion to salt. And so like we had just like pages and pages of problems about like slug farms. Yeah, it was kind of funny. Okay, so we have 2,880 meters of fencing to enclose a rectangular piece of grazing land, and then we want to subdivide it into 3 sections, and we don't need any fencing along the river. So I'm just going to use a red line to show that I'm not building a fence there. And then let's label all our other lengths. So in this case, X is, it already tells us what X is. It's the length of one side. So we would call that the width of the overall rectangle, just because it's the shorter side. So I'm going to label X, X, and X. And then what do you want to label the length?
2880 minus 4x.
Good. So that's the way I usually think of these, is like I have this much fencing, and I have to use 1, 2, 3, 4x of fencing, 4x feet, meters of fencing to make those vertical sections. And so what I have left for the length is just what I started with minus what I used for those vertical spaces. If that doesn't make a lot of sense, you can always label that length y and then say like 4x plus y has to be equal to that 2880. And if you solve that for y, you get that same 2,880 minus 4x. Okay, now that we have it all labeled, I want you guys to write a function for the area, right? Because we're trying to maximize area, which means we need an area function, and then go ahead and maximize. Well, I guess they ask you one more question in between, but
Because it's about as bad.
I know. So it's for Thursday, so it's not due tomorrow, but you want to do test corrections on a separate sheet of paper. So any questions that, so if it has a score next to it and the number on top is smaller than the number on the bottom, that means you lost points on the question. So if it says like 5 out of 6, then you lost points. So any problems that you lose points on, you want to redo in their entirety. Don't just like change bits and pieces, because then you don't get the benefit of going through the entire problem correctly from beginning to end, right? You'd rather, like, you want to put just as much work into doing it right as you did into doing it wrong, so that that's what you remember. So on a separate sheet of paper, and then staple it to your original test, and you'll turn that in on Thursday. So this is a homework grade. It doesn't like change your test grade, but one of the most important things in mathematics is understanding where you made mistakes. Like that's how you learn, is screwing things up and then fixing them, like most things in life. So we always want to go back and look at what we did and make sure that we know how to do it correctly, because similar problems are going to show up on the final. So I will give you back your tests, and then tonight you've got a couple video homeworks and a few after class assignments as well.
Oh, hello, okay.
I got it. Yes. Okay, thank you.
Yeah.
And you'll be here at 7 tomorrow?
I'll be here at 7 tomorrow. And then today, it's Tuesday, so it's the day I have my meeting at 11. But my all-star will start at 12.
Is that my grade down way?
So your grade on the final will replace your grade on your lowest test grade.
Wait, say that again?
If you do better on all your do better on the final than all of your other tests.
Yeah.
Your grade on the final will replace your lowest test grade